Okay, so the first part of this question is asking me, well, if we have a line, I guess it's asking how many vertices it has and how many edges it has. So this isn't a infinite line like in the previous part. This is actually just a line segment, which is essentially is just a closed line. And for this part, it's pretty simple. We have the number of edges is 1 and the number of vertices is 2. You can think about a line segment like a 2 or even just one-sided shape. So triangle would be an example of a 3-sided shape, and then if you have only 2 sides, it's kind of hard to make that, and if you have a one-sided shape, well, that's just the line. So we'll just say there's 2 vertices. Okay, now we're extending this into the second dimension. So if we now have a square for this, we have 4 vertices and 4 edges. Number of edges equals 4. Number of vertices equals 4 as well. A cube, well, we can draw it out. And we should see that there are 8 vertices, I believe. If we don't forget about this one at the back. Right, so there's 8 vertices and there will be 12 edges. And then a tesseract, I think that's a 4-dimensional cube. So it's quite hard to imagine it. Maybe we can think about its formula. I've seen a few pictures of it. I'm pretty sure it goes something like this. So we have the cube on the inside, maybe something like this, and then we just have a larger cube surrounding it. Although this doesn't make much sense because this is a 3D interpretation of it, isn't it? But if we connect those lines out to here and put the 4th corner somewhere over there, I believe it looks something like that. So the number of edges, I'm going to assume, is going to be 12 plus 12 plus 1 edge connecting each vertex of the smaller cube to the larger cube, which would be 12 plus 12 plus 8, I believe. So that's going to give us 32 in total. And the number of vertices, again, I don't actually know how accurate this image is, but I'm just going to say it's 16. So let's see if we can see some kind of pattern. We went from 1 to 4 to 12 to 32. And for the vertices, we went from 2 to 4 to 8 to 16. So at least for the vertices, I think there's a clear pattern of having 2 to the n. And perhaps using the number of vertices, we could figure out a formula for the edges. Okay, so for part B, again, I'm just kind of going off of the pattern we see here, and I'm not entirely sure how to justify it. But, okay, so it says conjecture, so we don't have to actually prove it. So my conjecture would be the number of vertices. This seems to increase pretty steadily, 2, 4, 6, 8. So I'd say this is 2 to the n, where n is the dimension of hypercube. Right, so if in the 4th dimension, the tesseract, we would have 16 vertices, which we could kind of see there. And now for the number of edges. Okay, so what I'm thinking is every single vertex will have, well, in the 3-dimensional case for the cube, let's just draw it out over here. Oh, this is a bad drawing. Let's do that. Okay. Okay, so in a three-dimensional case, each vertice is connected to three other edges, right? That makes sense. So for example, this vertex here is connected to this edge, and this edge. For two-dimensional case, each vertex is connected to two other edges. And so what I'm thinking is, using a number of vertices, we might be able to derive a formula for the number of edges. So the only problem is we can't just multiply it by n because these two will end up sharing an edge. And so I wonder if there's a way to uniquely identify one edge to one vertice, or maybe two edge to two vertices. Okay. Right, so if we assign them like this, and now this, finally, okay, that's repeating. So by putting a vertice at each opposite corner, we're able to assign three edges to each vertice and have them not overlap. Okay, that's interesting. So for example, in a 2D case, the opposite corners would be these two. And for the four-dimensional case, what would the opposite corners classify as? So if we look at this, for example, we have the 4 coming out here, but now this one, we can't, it would end up overlapping. I suppose one would be over here, that classifies an opposite corner. And we go like that. But again, this doesn't seem to be a very robust strategy, so maybe it's better to just take all of the overlaps and then figure out how many are actually going to overlap. Okay. So let's start in the 2D case. So if we assign each vertice to have two edges, then we're going to end up with each vertice is going to have at least one edge overlapping. So that tells us number of vertices is going to be, well, it's going to be 2 times the number of edges. That's what we're trying to work out. The number of edges is going to be 2 times the number of vertices, but then we have to subtract the number of edges again, or is that the wrong thing to do? I think we were meant to subtract the number of vertices, because each vertice will have one edge overlapping, so this is essentially that. And hang on, this formula doesn't even work though. Oh no, it does, because now we have, that's equal to the number of vertices, which is equal to 4. Okay, let's see if we can do a similar sort of thing in the 3D case, and then let's try and extend that to higher dimensions. So if we assign 3 edges to each vertice, we'll see every single vertice will have well, how many edges is it going to have in common? Ooh, this is actually weird. Number of edges. See, every single vertice has 3 edges, but now we need to count the number of overlaps. I mean, at first it would seem there's 3 overlaps for each case, but that would just take away everything. So we need to Okay, so let's start off with 3 multiplied by the number of vertices. Okay, maybe if we think about it differently. Okay, think about it like this. For each vertex is going to end up intersecting half of the other ones, right? So for all lines, at least half of them, or precisely half of them, you could say, are going to be intersecting because each line is accounted for twice. Okay, this is making sense. So each edge along the cube is being accounted for twice by these vertices. Because if we assign 3 edges to each vertice, every single edge on this cube is going to be accounted for by exactly 2 vertices. So therefore, the number of edges is just going to be n, where n is the dimension. So for in this case, it was 3 multiplied by the number of vertices over 2, because every edge is accounted for by 2 I'll call these mini or sub edges of the vertex. So here's my formula, and then we can use the previous 2 to the n we used for number of vertices to just get n multiplied by 2 to the n minus 1. And this is actually consistent with with what we observed over here. So we'll try it for the 4-dimensional case. Number of edges when n equals 4 is going to be 4 multiplied by 2 to the 3, which is 32, which is what we got. So this is my conjecture for the number of edges and the number of vertices. I'll just write number of vertices over here as 2gn. Okay, there's my solution for part B. I actually realized I forgot to start the timer, so let's just give myself 10 more minutes. Not actually sure how long I've spent, but I'll try and finish this in 10 minutes. Can you give the coordinates of the vertices of a tesseract where 4 edges coincide with the coordinate axes? This is weird. Oh, okay, so that's another way of thinking about the tesseract. So in 2D, our cube, if we drew with one corner at the origin, we'd have 2 edges intersecting with the axes. In 3D, sorry, this is a square. In 3D, we draw another unit cube and we'd have 3 edges intersecting with the axes, like so. And so in 4D, if I can somehow draw 4 dimensions, maybe I'll just do that. Something like that. It doesn't actually make much sense, but these would essentially be the bases of our cube. And then we would just draw it up like that. And you can see, what's the question asking? Can you give the coordinates of the vertices of a tesseract? So if we let x be the length of a side, we know for all hypercubes, all sides are the same length. Any of the hypercubes edges. So in 2D, if we start at 0, 0, if we start at the origin, one edge would be x0, xx, and 0x. For a cube, the origin there, and then we have all the same for the first side over here. But then if we also increase into this dimension, we have, oh sorry, I should have made these 3-dimensional now. And the z-axis, it's actually wrong, but I'll take it to go this way, just for convenience. And so I suppose we could actually get all of the since this is in 4-dimensional space now, there'll be 4 coordinates, and every vertex of a cube is either given by x or not x or 0, right? Because it's either going to have a 0 coordinate or it's going to be at x, which gives us these options x0, 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 x0. And this also confirms this conjecture up here, v equals 2 to the n, because now you can see there's going to be 2 choices for every single slot, and therefore there are going to be 2 to the n different, I'll call it distinct coordinates for the hypercube's vertex, and therefore the number of vertices is going to be 2 to the n. And yeah, this would give all of the coordinates of the tesseract's vertices. So I could just list them all out, but you get the idea. So the origin coordinate would be at 0, 0, 0, 0. Then you'd have a coordinate at x, 0, 0, 0. And then you might have one at x, 0, x, 0. And on. You're just putting all of the combinations into zeros and x's, which gives you 16 vertices. There we go. Okay, let's see the final part. What would be the longest length between 2 vertices? Okay, so I can see the answer, I think, to this question. Not exactly sure how you can prove it. Actually, no, I do know how we can prove it. So we have all of the length, we have all of the possible vertices here. Was this asking for the general case? Yeah, so I think this is asking for in terms of tesseract, but the general case isn't even that much harder. But essentially, we're looking for the longest distance between any of these 2 vertices. So we're essentially trying to maximize the distance between V1 and V2, where V1 and V2 are vertices of the tesseract. So we can say V1 is going to be of the form A, B, C, D, where A, B, C, D are either 0 or x. And similarly, we'll just define V2 to be the same sort of thing. Sorry, I should have made these all ones. Okay, so this is A1, B1, C1, and D1, and this would be A2, B2, C2, and D2. And so the distance between V1 and V2 would be given using Euclidean distance or Pythagoras high dimensions. We just use this formula, square root of A1 minus A2 squared plus B1 minus B2 squared plus C1 minus C2 squared plus D1 minus D2 squared. And obviously, if this was high dimension, you just add more, but it's the same sort of thing. And so to maximize this distance, what we can do is to maximize V1, V2, we want A1 to be equal to 0 and A2 to be equal to x, the non-zero number. Or it could, of course, be the other way around. It doesn't really matter, but we'll just assume A2 is greater than A1 without loss of generality. And of course, same kind of idea for all of these other ones, because if we're just trying to maximize the distance between them, because when we square it, all the signs are just going to get removed anyway. And so obviously we only have the choice of 0 or x. So if this was x, the distance between them would be 0. So we need one of them to be 0 and one of them to be x. And yeah, same idea for B, C, and D. So that gives us the maximum distance is going to be equal to x squared, well, because we did 0 minus x, when you square that, that's the same as x squared. So I'll just write x squared for each of these. And now we can combine these terms and simplify. So the maximum distance is 2x, where x is the length of one side. In a unit square, that would just be 1. And we could actually generalize this for any hypercube. Maximum distance between two vertices is given by the formula x squared plus x squared plus x squared, this n times, which is equal to nx squared, which is equal to x root n. So if n was 2, the maximum distance would be between these two, this diagonal, which is actually root 2x. And yeah, there we go. That is my solution. I'm actually pretty confident in this solution. I think this sort of made it clear that we could get the coordinates like this, and I'm sure we could use this to figure out the number of edges. But maybe that's the time. Maybe that's a choice for another video. I guess it would be something to do with these permutations, and then we'd multiply by n to count different sequences, something like that. But I'll check the answer now. This really didn't take too long, actually. And yeah, let's have a look at the solution. Okay, so at number 5, imagine forming a square by lifting a line segment up into the air. Okay, so we start with this line segment and then we just lift it into the air and create 2 new edges. Alright, yeah, that's interesting. It should be clear the number of vertices will be 2n. Okay, that makes sense, yeah, because we double, if we lifted this up, now we've essentially doubled this, and then if we brought this back like there, now I've created a clone of that with new vertices there. So yeah, the 2 to the n does make sense. The number of edges will be n to the n minus 1. Okay, yeah, so we did get that actually as well. And this result easily obtained if you consider the number of edges which coincide at a given vertex. Each edge has 2 endpoints. Yeah, so I think this is the same kind of idea here. If we assign for the dimension a number of edges to each vertex, it will be clear that each edge on the hypercube is accounted for by 2 vertices. So we just divide everything by 2 to give us this final result. Okay, coordinates of vertices will be all coordinates consisting of 0s and 1s. Okay, so in that case they used a unit cube, so it's fine. Just set x equal to 1, and then we just get a bunch of 1s and 0s, which gives us all our combinations. And the longest diagonal will be of 2 because it goes through the origin and 1, 1, 1, 1, which is what we proved here. If we set x equal to 1, then we get 2 over there. So yeah, I'd say this was a pretty good question. It was a bit shaky at the start, but once we got into it, I was able to prove some things quite nicely. So thanks for watching, and see you guys in a future tutorial. Bye.